Hey there, welcome back to part three of our unit here that's on solutions. In this particular part of the unit, we are going to be dealing with concentration and kind of what goes along with that. Let's see if I can get this to, what is it doing here? Why is this up here? There we go. So we're taking a look at solution composition. So in the last unit, little video, we were looking at yeah, electrolytes in solution and ions present in solution and all that sort of stuff. And then we introduced the concept of strong and weak acids and how those relate to electrical conductivity. So in this particular unit, we're going to take a look at a different way of quantifying what's happening in a solution, and that's called concentration. I know you've heard of that particular phrase before. One of the things I really want to make sure that we're really careful on here is that solution concentration is not the same thing as saying strong and weak. We use those terms a lot in our everyday language, when we're talking about how strong our orange juice is, or like that, whatever that is in front of it, is like Kool-Aid or something. It's actually a real chemical, but if that were Kool-Aid, you would say that the Kool-Aid on the left is weak and the Kool-Aid on the right is strong. We need to be very careful about how we use those particular words. The words strong and weak in chemistry specifically refer to how many ions are being released. If something is an ionic compound, especially an acid and a base, if it ionizes completely, that's a strong acid. If it does not ionize completely, that's a weak acid. Concentration is something else. Concentration is a measure of how much solute is present in the solution. So if you think about it with sugar, that's an easy place to start, right? One spoonful of sugar in there is not very concentrated. It's dilute. There's a lot of water and not very much of the solute. If we keep adding sugar to it, right, that solution is going to get more and more and more sweet. There's going to be a bigger ratio of solute to solvent, and we would call that concentrated. It's easy to do this with colorful solutions because you can actually see the difference, right? If it's just sugar water, you really can't see, or salt water, right? You can't see it. So not every ion is visible, whether it's dilute or concentrated. So a lot of times we use colored solutions to kind of remind you that there's something else going on. But this is not the same thing as saying strong and weak. So for example, salt is strongly ionic. When you put salt, sodium chloride, in water, it completely dissociates. 100% of the sodium ions and chloride ions completely separate from one another. Now that is true whether or not I put a pinch of salt in there or whether I put like a bucket of salt in there. I can have just a pinch of salt. It can be very dilute, but yet be strongly ionic, versus a whole bunch of salt in there and have it still be strongly ionic and now concentrated. So again, strong and weak relates to the number of ions that are present. That's more of a conductivity thing than it is about a concentration thing. So be careful with language when you're describing solutions. We don't want to talk about a solution being a strong solution or a weak solution unless we're talking about conductivity, unless we're talking about acids. So again, we're going to use the phrases dilute and concentrated. Those are the two words that we are going to use to talk about our solutions. So if we're going to talk about it mathematically, rather than just sort of conceptually, the way that we talk about this mathematically is a concept known as molarity, Molarity. It's related to moles, molarity, right? And that's why it's called that. So there are other ways to calculate concentration as well. So be careful if you're Googling stuff, but we are going to stick with the concept of molarity, Molarity. There's molality, normality, there's a variety of other ones. Be careful. So molarity, if we want to talk about how concentrated a solution is, you guys know that if we have more salt in the water, that's a more concentrated solution. Well, if we're talking about more salt in the water, that's the moles of solute. It's not just purely grams of solute because, again, different types of solutes have different molar masses. So we can't use it just straight on mass. We really want to know how many ions are present, how many moles of ions are present. So it's moles of solute, moles of the salt, so to speak. And then it's divided by definition, liters of solution. It's always divided by volume, and that volume is always in liters. You cannot do it in milliliters. So keep that in mind. When we do molarity, concentration of solutions, it's always represented in the units of moles per liter. And so you can kind of see I've got the units written here on the screen. The abbreviation for molarity is a capital italic M. And it's always kind of tilted, so I can do italics here. When I'm drawing it, I usually kind of draw it some goofy thing like that. But it's in the units of moles per liter. So the couple things, again, to be careful with, it is always moles of solute, the stuff that's being dissolved. This is always in liters. And note that this is liters of solution, not liters of water. So it's liters of solution. So if you maybe think about taking like a half a cup of sugar and a cup of water, right? When you mix those two things together, the final volume of the solution is more than the original cup, right? That sugar takes up some space. So when we're always doing our volumes here, it's always the final volume, the volume of the mixture, not the moles or the liters of water. So be careful with that if you see any trick questions on it. So the last two slides we've gotten here, a couple of examples of how we would apply this mathematically. So here we go. What's the concentration of a solution made by dissolving 20 grams of calcium nitrate in enough water to make 750 milliliters of solution? So whenever you see this, a couple of decoding points. Whenever you see concentration like this, that word means it's looking for molarity. That's what that means. Concentration is molarity. They're not going to say what's the molarity of a solution. They're going to say what's the concentration of a solution. So you've got to decode that. So I know I'm going to need molarity is going to be moles per liter. I always kind of write that every time I do these. So we've got 20 grams of calcium nitrate. So this right here, 20 grams of calcium nitrate, that is my solute. That's the stuff that I'm dissolving. It's always going to be dissolved in water. All of our solutions in this chapter are aqueous solutions. So we always know that this is going to be in enough water. And then we're going to make 750 milliliters of solution. This right here, that's our volume. So we need to do a little bit of conversion on these. This is a really common thing to have to do because our solute goes on top. It should be up here, right? But we need moles. And for our volume, that's going to go on the bottom, but we need liters. So you have to do two little conversions here to make this work. Very common with these, 20 grams of calcium nitrate. Calcium nitrate, that chapter still applies. You still have to balance your charges. Calcium's a 2+, nitrate's a 1-. Very common thing, you're going to have to do grams to moles conversions. You're using molar mass a lot. Basically, whenever they give you a solute, you might as well just start figuring out what the molar mass is. I should have had this prepared in advance. Calcium is 40.08 plus 2 nitrogens, 14.01 times 2, plus we have a total of 6 oxygens, so 16 times 6. So our molar mass of calcium nitrate here is, molar mass is 74.10 grams per mole. That's our molar mass of calcium nitrate. So first thing you need to do, convert grams to moles. I just do it in a little wonder fraction somewhere off on the side. 20 grams of calcium nitrate. And if I'm trying to convert it, I would do 74.10 grams equals 1 mole of this particular substance. So 20 grams divided by 74.1 equals this. 0.2, let me check sig figs. Looks like 3 sig figs up here is what I see, right? 2.699055, so it's 2.70 moles. Again, it's 2.6999, something along those lines. So I have to kind of round it to 3 sig figs. So that's my first part. That's going to go up here, right? That's my moles of solute. 0.270 moles. All right. I need liters for the bottom. So I'm going to take my 750 milliliters and convert it. So here's the long way, and I'll show you the short way. 750 milliliters, ml. 1,000 milliliters equals 1 liter. Basically, what you're going to end up doing is move the decimal place over 3 places, 0.750. You don't have to show this every time once you get used to it. But if you're not sure, you should check the one that students always do wrong all the time. If it's 75 milliliters, they forget to move the decimal place over all 3 places. So be careful if you're going to just do it in your head. 3 decimal places to move it over. So it's 0.750. 0.750 liters of solution. And notice how it says liters of solution. So then all I have to do is divide it. 0.7270 divided by, it would be 7500. I know, there'd be an extra sig fig there. Divided by 0.750. 0.750. It gives me a value of, there it is, 0.36. Check your sig figs, 0.36. I've got 3 sig figs up here and 4 sig figs, so my answer should have 3.360. You need to put that trailing 0 on there, and that's molar. So you can write your units of molarity either like this with the capital M, and this is read as 0.360 molar. That's one way to read that. Or you can write it this way, 0.360 moles per liter. Those are equivalent answers. They are both correct. So it's a 0.360 molar solution, or it's 0.360 moles per liter would work for concentration. Either one of those is appropriate answers. So again, the takeaways from this: convert grams to moles first. Put that up on the top. And on the bottom, it needs to be liters of solution. So you might need to combine volumes if they give you like liters of a solution and liters of something else. But usually they say liters of solution. Make sure that you're converting. Move the decimal place over 3 places. Here's our last one. This one gets a little bit trickier. This has to do with that idea of dissociation, separation of ions. So this one asks you about the concentration of ions that are present. Now, a lot of times what we really care about actually in chemistry is not the whole compound, but how many of a particular ion is present, because it's the ions that are actually doing the chemical reactions when we're combining things together. So here we have a question: what's the concentration of each type of ion when 12.8 grams of iron 3 chloride is dissolved in enough water to make 75 milliliters of solution? So here I did pre-prepare the molar mass of iron 3 chloride. So how do we do this? All right, molarity equals moles per liter. So how do we do this? This is going to be molarity of FeCl3 solution. That's what I'm working on right now. So first thing I got to do is I got to convert from grams to moles, right? So 12.8 grams of FeCl3 is 162.20 grams per mole. There we go, like that. So that would be 12.8 divided by 162.20 is not very many moles. It is 0.0789 3 sig figs. Yep, 0.0789 149 It's like, it's like messy stuff after it. So that would be 0.0789 moles. The liter 0 again is not significant. That's a placeholder. 0.0789 moles. There we go. And then we've got 75 milliliters of solution. So you've got to convert that from milliliters to liters. Move the decimal place over 3 spots. So it starts here. 1, 2, 3. There's another 0 in front of that. That's the one that always worries me, that students forget this. It's 75 milliliters, and 1,000 milliliters equals 1 liter. You've got to move it over 3 full decimal places. So this is 0.075 liters. So 0.0789 divided by 0.075, it's about 1 molar, right? Equals 1.05. We've got 3 sig figs in here. Molar solution. So that tells us about FeCl3. FeCl3. But this question doesn't ask about that. This question asks about the concentration of each type of ion. So there's a little bit of a different step, or a little bit of an additional step, I guess, that we need to do to finish this one up. Okay, so I'm going to erase. So I know that if I have a 1 molar solution of FeCl3, let's think about the dissociation of that. If I start with this, how is that thing going to break apart? This is the solid. When I dissolve it in water, it's going to separate into its ions. So what ions are present? Well, there's an iron ion, iron 3. There it is. I'm going to put AQ to say that now it's in solution. And I've got chloride ions. But remember, chloride ions is not this. That's not a chloride ion. That 3 is there because of balancing charges. It's chloride ions like this, AQ, and there are 3 of them. So you can think of this like a little Stoic problem. For every one of these, there are going to be 3 of these. So if I have 0.105 molar FeCl3, I know that one FeCl3 molecule is going to make 3 Cl ions. It's basically a mole to mole ratio. 1 mole of FeCl3 is going to give me 3 moles of chloride ions. So yeah, really all you're doing is you're multiplying it by 3, but you have to take into account those subscript numbers. So be really careful with that. So what this would mean, I'm going to move this out of the way so I can do my last bit. So we've got a 1-to-1 ratio here, and we have a 1-to-3 ratio here. So this means our molarity of our chloride ions is going to be 3.15 molar chloride ion, right? Because it's 3 times for 3 of these for every 1 of these. For our iron, that's actually an easy one. Fe3 plus, that's going to be seriously the same as the original one, 1.05 molar Fe3 plus, because it's a 1-to-1 ratio. So when you're trying to do ion concentrations, you're just looking at your formula. How does it separate? How does it break apart? And again, you have a sort of a mole-to-mole ratio that you can kind of think of it as a stoichiometry kind of thing if you want to do that. All right, so there you go. This is taking a look at concentration, kind of what is concentration, what does it represent, the difference between strong and weak versus concentrated and dilute. And then we looked at simple calculations of molarity, just a molarity of a solution, some of the little maybes that would kind of throw you off in there. And then we looked at concentration of ions. So by the way, a lot of times students don't know, and why would you? Like, how concentrated is concentrated, right? We're not going to talk about like saturated at this particular point, but how concentrated is concentrated? A 1 molar solution is pretty strong. If I gave you a 1 molar solution of hydrochloric acid, I would be requiring you wear gloves and goggles, coats and goggles all the time. A 0.1 molar solution of hydrochloric acid, not so bad. Okay, not so bad. The strongest that hydrochloric acid can ever get is about 12 to 14 molar. So just to give you an idea of kind of the range of values. So a 3 molar solution of chloride ions is actually really pretty strong. It's not like it's going to hurt you, but it definitely would be a fairly concentrated solution. So a lot of times in chem labs, we do solutions on the range of 0.1 to 1 molar solutions in our daily lives. So there you go. I hope you enjoyed it, and I will see you in the next one. We're going to go a little bit more in depth into using solutions. So there you go. Have a good one.